We're going to continue talking about Le Chatelier's principle, but we're going to now apply it to temperature. So we can still think about changing temperature with respect to Le Chatelier's principle of adding in something to their equilibrium mixture, right? And what we were going to think about is when we're increasing temperature, we are adding heat. So we're adding in heat energy to our reaction mixture. And basically, the reaction will shift away from wherever heat shows up in the reaction. So much the same way if we add reactants, a reaction would shift away from there. You add products, the equilibrium shifts away from the products. So if you're increasing temperature, you're adding in heat, so the reaction will shift away from wherever heat shows up. So for exothermic reactions, the heat we could think of as on the product side, right? Exothermic reactions produce heat, so heat is on the product side. So what that means is when you increase the temperature, all exothermic reactions will shift towards reactants. Endothermic reactions do the opposite because heat is on the reactant side. When we're writing or thinking about the reaction, right, that energy, or that heat is like a reactant, right? So you're putting in a more reactant, cause more of the reaction to happen, shift towards the product side when that equilibrium happens. So exothermic always goes to reactants, endothermic always goes to products when you heat it up. We can also decrease our temperatures, and then it's just the idea of removing heat, right? So in this case, when we remove something, Le Chatelier's principle says the equilibrium shifts to replace it. So in the case of an exothermic reaction, if we remove heat, cooling it off, right, decreasing the temperature, that would cause a shift to the product side. So we would always go towards the products if we have an exothermic reaction and we decrease the temperature. Endothermic reactions do the opposite, right? Decreasing the temperature removes heat. The equilibrium will try to replace it. So it would shift towards the reactant side for an endothermic process to replace that heat. So the sort of ordering of the, or direction of the shift is based entirely on whether or not the reaction is exothermic or endothermic. So we can apply this idea. Not only we can use it for making predictions and controlling reactions, but we can also apply it to analyzing a reaction. So I have this equilibrium, CO2 plus, so cobalt 2 plus reacting with the chloride to go to the COCl4. So we've seen this. So cobalt 2, just the ions by themselves, are pink. And cobalt chloride, or cobalt, the COCl4 2 minus, that complex ion, is blue. So what that means is, if you were to kind of move the equilibrium position, you would see different colors. So the reaction will literally look different colors. And we can see that when we heat it, heating turns blue, and cooling turns it pink. So we can see there's kind of these trends of these different colors. And so we can see where the equilibrium, or which side of the equilibrium is more common. Here, there's more reactants because it looks pink. And here, there are more products. It looks blue. Right? We're seeing the blue because the products are existing. So we can kind of use color or those properties to kind of monitor how has the equilibrium shifted. So we can do these kind of change the temperature, see how the equilibrium shifts, and then we can ask, is this reaction exothermic or endothermic? So our experimental results tell us heating the mixture turns it blue, cooling the mixture turns it pink. And so we know heating means we are adding in energy. The equilibrium will shift away from where heat is. So that would imply that heat is on the reactant side, right? Because the heating up causes a shift to blue, where we see more of the products starting to form. So that means we've shifted away from the reactant side where the heat was. Cooling does the opposite. It does the opposite, that you're going to shift towards the heat, which would be these reactants. So that means heat is on the reactant side. So both of these consistently suggest heat is on the reactant side. This is an endothermic reaction. So this is a common experimental technique you can do, where you take an equilibrium mixture, you heat it up, you cool it down, see how it shifts, and then determine whether or not the reaction is exothermic or endothermic. You can't figure out how much, you can't figure out like the value of delta H, but you can figure out the sign. And this is just kind of a simple experiment here. The reason why this happens is kind of, why does this happen is a little different than what we've seen with Le Chatelier's principle. Changing the temperature does not change QC, like when you're adding in reactants writing products. And in fact, changing the temperature changes the Kc value. So we've always talked about Kc as an equilibrium constant. It's the single value that doesn't change as long as the temperature doesn't change, right? You have the temperature, right, of this change is going to determine what the new Kc value is. So if you ever change the temperature, you'll get a new Kc value, a new equilibrium will form, an equilibrium will be defined by a new equilibrium constant. Your mixture will shift to reach that new equilibrium. And so there's that sort of kind of change. So this is the only way that you change the Kc is from actually changing the temperature. And we can see that basically endo and exo just show opposite trends of the directions of the shifts. So one video down, participation 218. No questions in this video. Don't worry, we got plenty more. We'll see that after you take care of the participation. Don't forget the week 6 homework and the chemical equilibrium post lab due this weekend. If you have any questions, let me know. Otherwise, just get started. See you in the next one.